Thermodynamics in Biosystem, Module 3, Energy, Segment 4, First Law of Thermodynamics. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about forms of energy, energy transfer, and mechanical forms of work. In this segment, we will discuss about First Law of Thermodynamics. So far, we have considered various forms of energy such as heat, work, and total energy individually, and no attempt is made to relate them to each other during a process. The first law of thermodynamics, also known as the conservation of energy principle, provides a sound basis for studying the relationships among the various forms of energy and energy interactions. Based on experimental observations, the first law of thermodynamics states that energy can neither be created nor destroyed during a process. It can only change forms. Therefore, every bit of energy should be accounted during a process. Let's consider a rock at some elevations which possesses some potential energy. Part of this potential energy is converted to kinetic energy as the rock falls, as shown in the left figure. Experimental data shows that the decrease in potential energy exactly equals the increase in kinetic energy when the air resistance is negligible. Let's consider a system undergoing a series of adiabatic processes from a specified state 1 to another specified state 2. Being adiabatic, these processes obviously cannot involve any heat transfer, but they may involve several kinds of work interactions. Careful measurements during the experiments indicate that for all adiabatic processes between two specified states of a closed system, the net work done is the same regardless of the nature of the closed system and the details of the process. This statement, which is largely based on the experiments of Joule in the first half of the 19th century, cannot be drawn from any other physical principle and is recognized as a fundamental principle. This principle is called the first law of thermodynamics, or just the first law. A major consequence of the first law is the existence and definition of the property total energy. Considering that the network is the same for all adiabatic processes of a closed system between two specified states, the value of the network must depend on the end states of the system only, and thus it must correspond to a change in the property of the system. This property is the total energy. Note that the first law makes no reference to the value of the total energy of a closed system at a state. It simply states that the change in the total energy during an adiabatic process must be equal to the net work done. Therefore, any convenient arbitrary value can be assigned to a total energy at a specified state to serve as a reference point. Energy balance. The conservation of energy principle can be expressed as the net change in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system during that process. This relation is often referred to as the energy balance and is applicable to any kind of system undergoing any kind of process. The determination of the energy change of a system during a process involves the evaluation of the energy of the system at the beginning and at the end of the process, and taking their differences as shown in equation 319. Note that energy is a property, and the value of a property does not change unless the state of the system changes. Therefore, the energy change of a system is zero if the state of the system does not change during the process. Also, energy can exist in numerous forms such as internal, kinetic, potential, electric, and magnetic, and their sum constitutes the total energy of the system. In the absence of electric, magnetic, and surface tension effects, the change in the total energy of a system during a process is the sum of the changes in its internal, kinetic, and potential energies and can be expressed by equation 320. Most systems encountered in practice are stationary, that is, they do not involve any changes in their velocity or elevation during a process. Thus, for stationary system, the changes in kinetic and potential energies are zero as shown in the right figure. Hence, the total energy change reduces to delta E equals to delta U for such systems. Mechanism of energy transfer. Energy can be transferred to or from a system in three forms: heat, work, and mass flow. Energy interactions are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a fixed mass or closed system are heat transfer and work. Heat transfer to a system or heat gain increases the energy of the molecules and thus the internal energy of the system. Heat transfer from a system or heat loss decreases it since the energy transferred out as heat comes from the energy of the molecules of the system. Work transferred to a system or work done on a system increases the energy of the system, whereas work transfer from a system or work done by the system decreases it since the energy transferred out as work comes from the energy contained in the system. Mass flow in and out of the system serve as an additional mechanism of energy transfer. When mass enters the system, the energy of the system increases because mass carries energy with it. Likewise, when some mass leaves the system, the energy contained within the system decreases because the departing mass takes out some energy with it. Noting that energy can be transferred in the forms of heat, work, and mass, and that the net transfer of a quantity is equal to the difference between the amounts transferred in and out, the energy balance can be written more explicitly as shown in equation 321. The direction of energy transfer is described by the subscripts in and out. The heat transfer Q is 0 for adiabatic systems, and the work transfer W is 0 for systems that involve no work interactions, and the energy transport with mass is 0 for systems that involve no mass flow across their boundaries. Energy balance for any system undergoing any kind of process can be expressed more compactly as shown in equation 322, or in the red form as shown in equation 323. For constant rates, the total quantities during a time interval are related to the quantities per unit time as shown in equation 324. The energy balance can be expressed on a per unit mass basis as shown in equation 325. Energy balance can also be expressed in the differential form as shown in equation 326. For a closed system that does not involve any mass flow across its boundary, the energy balance for a cycle can be expressed in terms of heat and work interactions as shown in equation 327. The net work output during a cycle is equal to the net heat input as shown in the figure. In the next segment, we will discuss about energy conversion efficiencies. Until then, I am Yusuf from Institute Teknologi Bandung.